All right. It is important for you to understand, more than anything else, that covalent bonding is all about the sharing of electrons. Not only that, but it also applies to a very small portion of the overall elements, the nonmetals. So if we're talking about electrons and we're talking about covalent bonding, we're addressing the nonmetals. And if you see on this poster, okay, the nonmetals are just this pink portion right here. So these are very important ideas when it comes to bonding, covalent bonding, that there's the sharing of electrons and that they are mostly nonmetals. The example I'm going to give you this morning is H2O. I want to show you how this molecule bonds. So let's start with the formula H2O. This means there are 2 hydrogen, 1 oxygen. We don't write the ones. We don't write this as H2O1, though we really could. It's just that that's not what we do traditionally speaking. But it's 2 hydrogens, 1 oxygen, a total of 3 atoms. All right, so we have this going on. Now the question is, how do they actually bond? So we have hydrogen, which has 1 valence electron, and how many valence electrons does oxygen have, Kelton?
7.
That's besides the fact that I think you just said 3 numbers. No.
Oh.
It's in column 16 on the periodic table. Daniel?
6.
That's 6.
Oh, yeah. Oh, yeah,
That
that one.
other number?
That I didn't say.
Not the 3 that you said before, right? All right. That's fine. Now, how many electrons does oxygen want? Justin? No. Hydrogen wants dose. Oxygen wants 8. The octet rule, the rule of 8, the atoms are trying to achieve 8 with the exception of hydrogen. Hydrogen only needs 2. That's on the board over here. So oxygen needs 8. It has 6. It has to find 2 more. And in H2O, it gets those 2 from the hydrogens, 1 here and 1 here for a grand total of 2 additional electrons. So the way this works is oxygen kind of comes over here, and oxygen begins to share a little bit, okay? So the hydrogen comes over here, and oxygen says, can I move that? Nope, can't move that one. It's going to take 1 electron, and it's going to move it down, and it's going to share it, okay? 2 electrons form a what? Yeah.
Happiness.
Well, sort of. 2 electrons form a, starts with a B and ends with ond. They form a bond. Excellent. 2 electrons form a bond. Bullet point number 5. Same thing is true over here. This hydrogen, okay, the electron kind of gets moved to the other side, and it shares an electron here. And so there's these bonds that form. When this is all said and done, move this up. When it's all said and done, it will actually look something like this. You have oxygen here. You have a bond with hydrogen there. You have a bond with hydrogen here. And oxygen ends up with its 4 remaining unshared electrons kind of down near the bottom. And I actually have a physical model that I can show you this on over here. Kelton.
In high school chemistry, my brother brought home this thing, and it had like hexagons.
Okay.
Could you put that inside one of those hexagons?
I don't know.
What?
I'm not exactly sure to what you're referring.
I don't know either.
Great. Let's continue. This is a water molecule. You'll notice that it is bent in nature. Okay, this is actually called a bent molecule. Some molecules form lines. For instance, like this one here, this is CO2. Okay, you'll notice the carbon is typically black in these models. So we have carbon in the center. We have oxygen, which is red, so CO2. This is H2, so the two whites are hydrogen, O. So we see two oxygens in this molecule, one oxygen in this molecule. Notice it's bent. Water is bent, okay, like this. The reason it's bent is these electrons are all negatively charged, and as a result, they're repelling each other. So they're pushing these bonds up. That doesn't happen in CO2. Okay, CO2 has got a double bond here and a double bond here. All of the electrons are lined up in a line. So it forms what we call a linear molecule. It means it's straight up and down, like a linear equation. It forms a straight line. This is bent, though. Now, the bent nature of water is quite unique. If water wasn't bent, it wouldn't expand when frozen. The reason it expands is because this molecule is bent, and the way it interacts when it turns into a solid forces pockets, which causes the ice to expand, to be bigger or less dense than its liquid counterpart. So the bent nature of this is why water or ice expands. Okay, it's also why water has a slight charge to it. So if you bring a really strong magnet or electrical current near a stream of water, it will bend towards the magnet or the electrical current. That's because water is bent. CO2 can't do that because it's linear. This bent nature of water is really quite unique. It's also why most of our body is made of water, and that because there's water in our body, when combined with other minerals and vitamins in our body, it can conduct electricity, which means that our body can communicate to our muscles and organs and things because water is bent. So this molecule having this bent or U-type shape is not just not important, it's really important. As a matter of fact, it's crucial to how water behaves. If the polar ice caps didn't expand, ice didn't expand and ice didn't float, the whole world would be underwater because all of those ice caps would sink and all the water would go up and there would be no land. So this one molecule arrangement is basically what keeps our Earth from flooding. Okay? It's really, really important. So water is bent. Make sure you note this. You'll have to recall it on your test. All right. Let's move on. That's our covalent review. We're going to move on to ionic bonding today. Ionic bonding is not as nice as covalent. Covalent's all about sharing and trying to get along. And ionic bonding is all about theft and stealing and aggressive behavior. So, it's all about theft. So like covalent bonding is about sharing, ionic bonding is about theft. All right. The other thing that it's really all about is unlike the covalent bonds, ionic bonds are all about metals. Ionic bonds are about theft and about metals. Okay? Covalent bonding, non-metal focus. This is crucial. When I give you a sheet of 50 of these things to name, okay, without memorization, there's no way you can memorize it. When I give you a sheet of 50 of these compounds, you have to name. They're super easy if you know one and only one thing. What are the metals? What are the non-metals? So, my poster. Ionic bonds start with metals. Covalent bonds start with non-metals. They have different naming schemes. You name ionic bonds different than you name covalent bonds. So when I ask you to name 50 of these compounds and I mix them all up and I give you a sheet and it takes an entire class period to work on, your success Your ability to do this will rely entirely on your ability to name metals and nonmetals. And I will not give you this chart for the test. You have to know which are metals and which are nonmetals. It's not hard. Everything that's green is a nonmetal. Hydrogen and the pink are nonmetals. Metal, nonmetal. You will not need to worry about metalloids. Yes, Kelton.
Never mind then.
Okay, so the ionic bonds, okay, Izzy?
So will we have to memorize like all of the metals and metals?
Well, it's not hard. If you see an element and it's over here, you should just know it's a metal.
Oh, we're gonna get a periodic table.
You get a periodic table, it will not have anything other than just the symbols on it. It won't tell you what's metal or not metal.
I thought you were saying like we had to memorize every single.
No.
What's metal?
How many elements do you have to memorize? No. 10. Okay? 10. So I won't ask you to memorize it. You'll get a periodic table. You just won't be told what's metal and non-metal. You have to know that. Okay?
So we're gonna get a metal.
You'll get the same periodic table I always give you for tests. It's this one.
Oh, Mr. Bucket.
Okay? All right. So ionic bonding, theft, metals. It's about the metals. So let's go ahead and take a look at how this works today. Make sure you pay close attention to this process because it's all about ions. So we're drawing on everything from Unit 1 back in September and October because we build on everything. All of that stuff we learned in the first 2 units is going to come back into play now. So let's go ahead and begin. Where the whole focus of this type of bonding is ions. Okay, so remember when I had you tell me what is an atom, what is an ion, what is an isotope? The ion is the important factor here. Okay, ions play an incredibly important role in a type of bonding, okay, and a very common type of bond because it applies to all the metals. So, ions are charged atoms, if you can remember. Some common ions you will see, okay, in this bonding unit will be hydrogen, which would be plus. You would see something like lithium, which is plus. Now, hydrogen is not a metal, okay, but it does form an ion that is important, so I will bring it up. But lithium, sodium is a plus. Magnesium is a plus 2. Oxygen is a minus 2. Fluorine is a minus 1. Chlorine is a minus 1. These are charged atoms. They have a charge. What makes the charge possible? Justin? The electrons. That is absolutely right. If they're positive, they've lost electrons. Okay? If they're negative, they've gained electrons. Remember, that's kind of counterintuitive, right? We think of gaining as being a positive thing, but when it comes to electrons, they're negative charges. If you gain a negative, you've become more negative. You've gained an electron, you're more negative. You've lost. Now you have more protons, you're more positive. Charged atoms. These are ions. When you have ions, they form bonds because opposites attract. Positives like negatives. They form bonds. So metals will form with nonmetals. Notice that if I exclude hydrogen, and I will for just a second here, these are all metals. Metals form positive ions. These are all nonmetals. They form negative ions. Positives like negatives. Opposites attract. So they will form bonds. They will form ionic bonds. Metals and nonmetals like to form bonds, okay, through this opposites attract paradigm. Let's go ahead and look at this in more detail. All right. Let's take sodium chloride, classic table salt. Sodium, typically speaking, is in the first column. It is in the first column, not typically. It is in the first column. It's an alkali metal, so it has 1 valence electrons because it's in the first column of the periodic table. Now, sodium, being a metal, and oftentimes having its electron ripped and stolen away, will form a positive ion. We'll get to that in just a second. But it has to be bonded with an aggressive nonmetal, all right, which will do the ripping off. And then a really aggressive metal or nonmetal would be chlorine. So chlorine has 7, greedy little bugger. And this is not like it is in covalent bonding where the hydrogen comes over and says, hey, I'll share one. And chlorine says, hey, I'll share one. And they form this cute little covalent bond. That doesn't happen here. Chlorine sees sodium and says, ooh, I want your electron. I'm not going to ask nicely. I'm just going to take it and rip it off. And that's what it does. Okay? So it rips it off. Rips electron off. Sodium. It rips it off. It steals it. But this is a multi-step process. Hang on, Izzy. This is a multi-step process. As a result, sodium becomes positive. It's lost a negative charge. It becomes positive. Chlorine will become negative as a result of this process. Sodium becomes positive 1 because it lost 1. Chlorine becomes negative 1 because it gained 1 negative charge. If we were to look at the breakdown here of protons and electrons, sodium starts with 11 protons. That's what makes it sodium. Chlorine starts with 17 protons. That's what makes it chlorine. Those numbers can't change. Sodium had 11 electrons, but it had 1 ripped off. So it now has 10 electrons. Chlorine had 17, but it stole 1, tucked it in its pocket, won't give it back. That means it has 18 electrons. There's now no longer a balance here. There's more protons here. There's more electrons here. So this is more positive, this is more negative, and as such, we end up with these 2 ions, a sodium ion and a chlorine ion, and what ends up happening is this +1 and this -1, they're like, ooh la la, I like that. Ooh, I like your positive, and the other one's, oh, I kind of like your negative, and they're like, oh, and they sync together, and they form this ionic bond, and we call that NaCl. And that is table salt. Izzy, your question.
So all of these gases, they want to be negative?
They don't want to be negative, no. Chlorine wants electrons. As a result of wanting an electron, it will become negative.
But if they want an electron, doesn't that mean they want to be negative?
No, it just wants 8. It wants to be happy. As a result, it becomes negative.
But it has 18.
There is a, Izzy, yesterday and the day before I very specifically said valence electrons are not total electrons. Valence are just the outer shell. Total electrons, some are tucked way deep down inside. So in the original notes, I had you draw the atom and I had put a bunch of dots near the nucleus. But there are still some floating on the outside. So the idea here is there's really 2 classifications of electrons. There's all the electrons, okay, and then there's the ones on just the outside. These, all the electrons, help to show us the balance that either creates an ion or creates a stable atom that has no charge. But in order to achieve 8 valence electrons, this will gain 1 and this will lose 1. And your question is a good one. It's one that I get just about every year I teach this. And so I'm glad you asked it. Okay, she's right. And it's important that you understand there are total electrons and then there are valence electrons. You cannot put them together. There are outer shell electrons, the ones on the outside of the atom. Those are the ones that mingle with people. Hey, George, how you doing? Hey, you over there, you want to come join us? Bond up? Okay, nope, all right, fine. Yeah, you. Okay, these are the ones on the outside. Then there are the introverts. Did he see me? Did he see me? I'm going to talk to nucleus. I'm going to go stand next to the nucleus. I don't want anyone to see me. Oh my gosh. Did you see that electron? It wanted to bond. Oh, I got to stand over here, get away from it. Okay, I'm just going to stand here and huddle and do this because I don't want to bond with anything. Those are all the ones tucked inside. You've got your extroverts on the outside of the atom, and you got your introverts on the inside. Okay, your extroverts are the ones that do all the bonding. Hey, you, come on over here. Oh yeah, cool. Link up. We bonded. We good. Okay, that's how that one works. Okay, and if it's mutual, they want to bond. That's like sharing. That's like covalent. Or there's like, hey, you, come here. No, you don't back down. Come here. Gotcha. That's right. Who's the man? I'm the man. I got you. You can't have it back. No, you got to come get it. Bond, ionic bond. There it is, because it was stolen. Okay? So they're sharing. Hey, George, you want to link up? Yeah, sure. Okay, mutual. And then there's, you come here. Boom, stealing it. That's ionic. It's very aggressive. Okay? This is covalent and ionic bonding. See, the metals, you can think of it as kind of like heavy metal, metal rock, like metal music, right? Like tough, mad, okay? That's ionic bonding. Then there's covalent. It's a soft, cozy kind of bonding. Kind of got the sharing thing going on. Okay? So, let's do one more example. Sodium fluoride. NaF. Sodium fluoride, if you go home right now, which don't, if you were to go home right now, you would find sodium fluoride in your toothpaste. Look at the back of your toothpaste. It's an active ingredient. It's a plaque fighter, kills plaque. That's why you get fluoride treatments. It's not pure fluorine. That would eat your teeth away, and then it would dissolve your bottom jaw, and your face would disappear. No, you wouldn't want that. What we do is sodium fluoride. Okay? Sodium fluoride is what kills plaque. It's when you get fluoride treatments. It's very aggressive. It'll go after things, nastiness in your mouth. Okay? Sodium fluoride. It's the same process as sodium chloride. Sodium has 1 valence electron. Fluorine has 7. Okay? So what happens is that fluorine says to sodium, come here. There it is. Okay? Takes the electron. As a result, sodium again becomes positive. Fluorine becomes negative. They see each other and they're like, oh, okay, opposites attract. NaF. Same process as NaCl, sodium chloride. It's all about the taking and the receiving and then the attraction afterwards. Yes, Miles.
Since covalent bonding is all like nice and sharing. And then ionic bonding is all.
Exactly. Yeah.
Then when ionic bonding happens, is there an explosion?
No, not necessarily. I mean, if we were to combine sodium and chlorine, it might be somewhat of a violent reaction, but then that's not always the case. I mean, it just depends. Calton?
Why does 8 electrons make an atom heavy? Why not 6?
Why not 6 or 7? The way that an atom is structured, electrons hold energy. Okay? Atoms are like onions. They have layers. Each layer has to have a certain amount of energy to stabilize the atom. So depending on how many protons that particular atom has, and depending on how many electrons it has, there's this mutual stability that you're trying to achieve. Noble gases achieve this naturally. Okay? So it's all about kind of this balance of energy. When you have an atom that only has 1 electron out there, it doesn't have enough energy to stabilize the atom. And so it's going to seek out energy, or it's going to try to get rid of that electron and kind of shrink in on itself. That happens. Okay? But ultimately, we're looking to create an outer shell. It'd be like if you were Mr. Potato Head, and you knew in order to be stable, you had to find 2 feet, 2 arms, a nose, some ears, eyes. You're trying to you don't want to just walk around as an empty spud. All right? So you're going to go around, and the only way you're happy is if you filled all of those slots with your ears, your nose, your eyes, your hair, your shoes, your arms, etc. If you're missing even 1 arm, You're going to do everything in your power to find that one arm. And if you're missing a bunch of stuff, okay, then you'd rather be an empty spud than malformed. And so it's kind of like Mr. Potato Head. You're looking to fill all your slots. And you will do anything in your power to do that because you're not happy, you're not stable, you're almost uncontrollable if you don't have these slots filled. Okay? Yeah.
Sometimes Mr. Potato Head's not a potato.
Yeah.
Soft taco shell. No, that was Mrs. Potato.
All right. Last example for today. We're going to do magnesium oxide. MgO. Magnesium has 2 valence electrons. So Mg has 2. Oxygen has 6. Okay? What happens here is, unlike with sodium and fluorine or sodium and chlorine, in this particular example, it's not going to be the stealing of 1, it's going to be the stealing of 2. Oxygen will rip 2 electrons off magnesium. This changes the way the ion is structured a little bit. Magnesium will not be a +1, it will be a +2. Oxygen will not be a -1, it will be a -2. Okay, it's all about the number of electrons undergoing this transfer process. Jacob.
This might be a little, actually, I'll just
Okay. I want to briefly break this down. Magnesium has 12 protons. Oxygen has 8 protons. Magnesium starts with 12 electrons. It's balanced, but it loses 2, so it ends up with 10 electrons, which means it has more protons. Hence the +2. Oxygen gains 2 electrons. It has 10 electrons. It's more negative because it has more electrons, hence the -2. When the +2 and the -2 see each other, they're like, oh, we can cancel each other out. +2 and -2 ends up 0. That's what we're going for here. So they join forces, opposites attract, and you end up with MgO. That's a pretty cool reaction. If you've ever seen me light magnesium on fire, it's incredibly bright. I've done it before in here. Correct. Magnesium combining with oxygen creates magnesium oxide. It's a white powder, and we call it MgO. Ladies and gentlemen, it's time for you to go. Okay, have a good day.